All right, all right, all right. We're right back into what we were doing last week. We're just continuing on. We're calculating conductor ampacities. Last week we got into talking about doing the taps, and like this one here, we're in 240.20 1B1. And as I said, and I'll rephrase this one more time, if you're doing a tap that's 10 foot or less, you divide by 10. All other
Yep.
taps you take at a third that are greater than 10 foot. And then if you have a transformer and a tap, you do the secondary to third or the primary to third. But when you get to the secondary, you're going to take it at a third, but you also need the ratio of the transformer. Okay. So
Sure.
we'll go through this real quick. This shouldn't take long. Everybody should have these taps down pretty well now. But here in the illustration, I've got a 600 amp overcurrent device upstream. I'm going to make a tap off of that feeder circuit that's going out. So I'm going to divide that by 10. That'll give me 60 amps. I go over, look at table 310.16. We're using the 75 C terminals. Come down the next size above at 65 amps, which is going to require a number 6 conductor. So therefore, we verified that the 65 amps is greater than the 60 amps. Therefore, the
Yep.
size THW and copper conductors are number 6. Very
Nice.
simple. Then I go to a 25-foot tap. We're in 240.21B2. I said everything else we take at a third. So I take 600 amps at a third. That's going to give me 200 amps. Once again, I go to table 310.16, 75 C column. Come down. You're going to pick up the next value equal to that. In this case, it's 200 amps. Come across the left-hand side, it's going to tell you it's a 3-aught conductor. So your size THW and copper conductors for this tap will be 3-aught. All right. Then we're going to go to the next one. This is where we actually have a transformer in the tap. And I said on the secondary, you got to get the ratio of the transformer. And in this case, we have a 408 volt primary and a 208 volt secondary. The upstream overcurrent protection device is a 300 amp. So when I'm doing the primary tap, I'll take the 300 amps at a third. That's going to give me 100 amps. Go to table 310.16. The next size above that or equal to that is 100 amps, which is a number 1 aluminum conductor. And this is a trick question here, because what will happen if you're taking the test, you'll look at the conductors we gave in this case, and we're telling you we're using THW and aluminum instead of copper here. Okay.
Okay.
So, and that'll be you got your first column, then you go over the next set, you'll see the 60, 75, 90 C over there, and that'll be your aluminum conductors. Okay. Now, when I look at calculating the secondary conductors here, I need the ratio of the transformer. So I'm just going to take the 208 volts divided into the 480 volts. Then I'm going to multiply from that point a third and the 300 amp overcurrent device. That's going to give you 231 amps. The next size up above that is a 350 kc mil aluminum. So as you can see, doesn't matter what you're doing, which conductors you're using here. All you have to remember when you're doing these calculations is if it's 10 foot or less, divide by 10. Everything else, take it a third. And if I have a transformer in the tap, I got to get the ratio of the transformer on the secondary. That's it. Okay.
Yeah, and it's important for guys out there when they're taking that exam to, like, it's easy, and I know this happened to me, is it's easy to try to just go too fast and not read, and just, and I was just as guilty as anybody. You have to remember to think of every little thing when you're doing this, as far as like the aluminum, just kind of like what James was saying. He throws that trick in there because, and I'm guilty of that too. I just think everything's copper, and then
Mm-hmm.
next thing you know, all of a sudden, the answer is on there for copper.
Mm-hmm.
So that's what you have to realize when you're taking that exam, is that the wrong answers are on there too, and they seem right because if you do the calculation, it'll come out to an answer that's copper, and so you just have to know that they're intentionally trying to trick you, and you just have to make sure. So that was just something I wanted to add.
Sure. And it is true. And that's why we bring this stuff up. And this one here, this is a 100-foot tap. And you'll notice we also put some rules in there, for how that would be installed, 30 foot up above, or the panel board and all this other stuff, and then 25 foot back and 40. So we put all that stuff there if you want to reference. But in this
Okay.
case, we got a 400 amp upstream. Take it at what? A third. Everything that's left
Yep.
at a third. That gives you 133.3. In this case, we're doing copper. So I'll go to table 310.16, 75 degrees C column. The next size above the 133.3 is 150. Come across. It's going to tell you that the size PHW, and copper conductors are required to be one off. Simple. And if
Nice.
you notice, I didn't change anything. I stayed the same process all the way through. I took a third for everything that was over 10 foot. The only difference I did was on the secondary of a transformer that's in a tap. I took the ratio of the transformer part of that calculation. Okay? So
Nice.
everybody should be able to understand taps pretty easily. I
Right.
always say a lot of times people overthink things. And when I was teaching people for Journeyman, Masters, whatever, I'd always give these little insights like that. Don't overthink it. Just remember these rules, like a rule of thumb. If you follow this, you can go find the information you need, but at least you know how that's supposed to be calculated. Okay?
True.
Now, this is where we get in. Now, they actually came in, I forget what cycle it was, but they come in, and a lot of people used to say, oh, just tap the secondary side of that transformer. Well, that didn't make it a tap. Those are actually uh, connections from the secondary of the transformer. Okay, so
Right.
they come in and they relayed this article out, specifically 240.21, and then that's why we have 240.21B and we have C now. And this one
Right.
here is where we got connections from the secondary of the transformer. Now, this particular one, we're looking at C2, and this is connections um, for 10 foot here. So when you go and you look at this, all you're going to do is like we've done before. All you're going to do is treat it just like we do a transformer calculation. You remember I did a presentation on here where I went through and just showed how to calculate transformers.
Yep.
This is the same thing for sizing your conductors. All you needed to know was the kVA of the transformer, multiply it by 1,000, put it in VA. Then you take the voltage. In this case, it's a 208 volt three phase, so I have to multiply the 208 volts times 1.732, which is going to give me 360, and I'm going to divide that into the kVA or the VA of the transformer is going to give me 194.4 amps. Well, if I want to size the overcurrent device for that, I'll go over and look at table 240.6A for the standard ampere rating. The next size above that's 200 amp. And then if I look at table 310.16, 75 degree C column, come down 200 amps is for a 3-aught conductor. So in this case, I just sized it real quick, said I need a 200 amp overcurrent device and 3-aught copper conductors. Okay.
Yeah, and this is kind of interesting too. I kind of wanted to ask you this question. So if you were to have that on the exterior of the building, what was the limit? What would be the limit of the tap conductor?
There ain't no limit. And we'll get to
Yeah.
the outside transformer conductors here in a minute,
Okay.
and we'll show
All
that
right.
calculation. All right.
10-4.
They're all the same calculation. Okay.
Right.
Like this one here, you're setting here, this is 25 foot. Okay. I do the same
Gotcha.
calculation. I've got a 200 kVA transformer. I'll multiply it by 1,000. It's a 208 volt secondary here with three phase. So I multiply it by 1.732. Do my calculation. The full load amperage is 555 point amps. The next size above that is a 600 amp overcurrent device. Now I'm going to parallel this one 3 times. Okay, we're telling you to do it 3 times. Well, a 3-aught's good for 200 amps. So three 200 amp uh, parallel conductors is going to give you 600 amps. And if you notice, did I change the calculation? No,
No, but you just
calculation's
have to
still
be
the same.
careful because if you just all of a sudden at the end of your statement put in an adjustable circuit breaker, then you're gonna have to change your equipment ground. So
Oh yeah, well, uh, that's somebody that is trying to find a problem that was never a problem in the first place. Good job, Paul. I heard that he took and was mouthing off about me again. Oh, hey, Paul, if one of you or your minions watch this, um, you need to go look. Maybe go look at the 70E committee, or you could go to the EECA committee, which covers NFPA 496, 497, 499. You'll see that I'm a member, and I have been part of the task groups that have done those. So to sit there and say I hadn't done any of this, once again, is nothing but a lie. Okay.
Sure.
And matter of fact, I was on there when they asked my dad to take and do um, uh, to clean up the hazardous location portion. They asked him to be the chairman. Well, you know why they asked him? Because he actually knew what he was doing when it come to the hazardous location field. And then he had new members that were put on, and they helped clean that up. Well, guess who was in charge, Paul, of getting all the stuff together for the task groups that were put together to do that? Yeah, Dad had me do it. So, when you come out and you're going to make all these false claims, you might want to get your facts straight instead of just mouthing off. And that seems to be
Sure.
what he does best at, is just mouth off about everybody. But
Well,
anyway,
he says you never asked your dad, or your dad never set you straight on any of these what he calls misinterpretations, but he's all over the place because he says an outlet's any point on the wiring system, and that's not true. So
well,
it is what it is.
the way I look at that is, does he honestly think I don't ask my dad these questions?
Yeah.
I mean, give me a break.
Yeah, that's funny. I had a
Okay.
good time.
So here's one. You'll notice there's no length here we're talking about, and these are the outside feeder conductors. Okay, where I'm going outside transformer. We even put a new transformer in, like you would see outside. We got a 750 kVA transformer, and you take and uh, look at that secondary connection. What is it? It's 480 volt. It's three phase 1.732. That'll give you 831 volts. You divide that into the VA of your transformer, gives you 903 amps. Now, remember in this case, and we covered this earlier, 240.4B deals with overcurrent devices 800 amps or less. Once I get over 800 amps, then I'm looking at 240.21C. In this case, my conductors have to be equal to or more than the overcurrent protection device in this point of what the load is. Okay, so that means I have to be equal to it or drop down. Well, I had a 903 output. I can't exceed it, so I have to drop down to the next standard size, which is 900 amp. And then I'm going to look at what type of conductors I need here. And in this case, I'm going to need 350 KC mil conductors, which I'm going to parallel 3 times, which is going to give you 920 amps. Okay, I just know that off the top of my head because I've done it so many times. But
Right.
what we like to point out here is make sure you know the sizing of your overcurrent devices and how you do it on the application of 240.4B and 240.4C. So once you
Yeah.
see it's over 800 amps, you need to start looking at how high it's going up, because you need to drop down at that point.
Yeah, and keep in mind, and we've had some guests on here. Big shout out to Reese, who we had as a guest on here. She had a little bit of a confusion when it comes to sizing the overcurrent device and sizing the conductors. So you have to keep in mind that when you're doing that, you have to keep the two separate, and you have to realize they're two separate things, and that's I think Reese had a little bit of a problem with that, but big shout out to Reese. I hope you you know pass your master, and
Sure.
that was
All right. Well, here's a busway. I'm going to tap from a busway. How hard is this? I said everything else you take at what? A third? So here's a busway tap. I've got a 150 amp busway, and I'm going to reduce it in size. What is the minimum? Well, I'm going to take it at a third. That'll give me 50 amps. So I have to have at least a 50 amp busway there for tap.
Yep.
I could go up to 100 amp. But once I get to 150, guess what? It's no longer a tap at that point.
True.
Okay? I just want everybody to know what the difference is in taps.
Do you remember that one do you remember that question that I did? Where I did the full size as the answer?
Oh, yeah. I remember it. Oh, looky here. Here's another one. Here's where we're doing a tap. We're going down to a motor here. Okay? It's 10 foot or less. What do I divide by? 10. If this was 25 foot, I'd take it at a third. So in this case, it was 10 foot or less. Divide by 10 gives you 80 amps. Now, if I go over and I look at table 310.16, I come down and pick up my 75 degree C column. The next size above that's 85 amps, which is a number 4 conductor. So therefore, the size conductors are required to be a number 4 copper. But if you notice, did I change anything that I've said up to this point about doing a tap? No. Kept it all the same. Did not do one thing different. Here's another one where I'm going over here and I'm doing the conductors from the generator terminals. Okay. I've got a 241 output. We're telling you that's what it is. How do I know that? Well, I've got a 200 kVA generator here, and I've got 480 volts. It's 3-phase, 1.732. Okay. And it'll give me 831 volts. Divide all that in, that gives me 241 amps. But now I also have to take that at 115%. So and people say, well, where do you get the 115%? Go over and look at 445.13. That's where you're going to get the information that I've got to put 115% on it. All we're doing is showing you in that illustration, how did I get that 241 amp output? Well, that's how I got it, by doing that calculation there. So take the 241 amps at 115%, it's going to give you 277 volts. And then I'm going to look at sizing this conductors. And the next size up above that is 300 kc mil conductors. Very simple. All of this is easy to follow. You just need to know where you're looking here. Okay. But the one thing I want to point out, when we were doing the secondary side of that transformer, the conductors for it, and then I'm doing it here for a generator, I still did the same calculation to determine what my full load amperage was. Okay.
Right.
Now, that got us through that. Now, what we're going to get into is looking at motors. Now, we're going to start this off a little bit different. All right. Everything I've done up to this point, I've based off of looking at 240.4B for overcurrent devices, 800 amps or less, and 240.4C. Okay. That was just how we went about the overcurrent protection devices, because sometimes we need to do that and to help us determine, make sure we're matching up with the size for calculating my conductor ampacities. This one here is going to be a little bit different, and this is going to be a prelude to what we're going to do in the next part, where we get into sizing overcurrent protection devices. So when you're looking at this, you would be looking over at 240.4G is where you're going to pick up your sizing for overcurrent devices, and these are going to be where you get over percentages that are over 125%. Okay.
Right.
So as we start to look at this is all going to tie in the same way. And the reason I bring up the overcurrent devices is because once I go to 240.4G, then I'm going to go look at 430.6A1. And you'll understand why I'm telling you this in just a second.
Yep.
When I look at 430.6A1, it says anytime, basically in a nutshell, this is what it's saying. Anytime I'm sizing my overcurrent devices and my conductors, I'll use one of the tables that's listed in tables 430.247 through 250. Okay?
Right.
So in this case, I've got, I'm going to size conductors here, and I have a 115 volt single phase, 3-phase design B motor. Okay? Well, since it's single phase, everybody should get used to this. If it's single phase, you're looking at table 430.248, and if I'm doing three phase, I'm looking at table 430.250 to get my amperage ratings. So basically, what
Nice.
I'm trying to tell you here is I'm going to use the amperage rating that's in the tables. Now, when I get over to AC units and refrigeration circuits, then you're going to use the nameplate. Okay.
Right.
And that's why we break this down. So you know where we're going to get these amperages. So in this
Right.
case, for that 3/4 horsepower single phase 115 volt motor in table 430.248, it's going to tell you it's good for 13.8 amps. And then I go to step 2, and you go look at 430.22, and where I have a single motor there, you have to take it at 125%. Now, if I have multiple motors here, you take the largest motor at 125%, and all the rest of the motors are at it at 100%. Okay?
Nice.
Now, for this one, 13.8 amps times 125% gives me 17.25 amps. The next size above that for table 310.16 in the 75-degree C column is a number 14 conductor. Simple.
Ooh.
Okay?
Yeah.
And what's going to be interesting about, I don't know what it is, I have to do it in my head or pull out and add it, but you're going to see you're going to have a much larger overcurrent protection device. Okay?
It would probably be number 14 on a 30.
Yeah.
My guess.
I'm guessing that's what it is, but I have to do it, add it real quick. Now,
Yeah.
this is part of our new illustrations that I really like how these are done, because we actually show you the control unit. We show you the disconnecting means, how it would look inside, how you hook everything up. We show the wires coming in, everything bonded in. I mean, it's fantastic. We even show the blue control wirings going down everything.
So right there, you're showing like 3 outlets, right? No, I'm just kidding.
Well, from what they're saying, who was it? I guess Ryan. He said it was at the load side of the disconnecting means, and then I proved them wrong on that, and then they changed their stance on that and moved it, I think, to the equipment, and then I proved them wrong on that, and then they moved it to where it just connects.
Now it's just floating in the peckerhead now.
Yeah, it's just floating in an infinite space. Unbelievable. But anyway, as we look at this illustration, your known values, you got a 2 horsepower single phase 208 volt motor. You don't need to know anything else. All you need to know is go over table 430.248 at single phase, get your amperage, and then put 125% on it and size your conductors. Okay, so that's your homework next week on that. This one here is a 3-phase, the exact same thing. I've got a 208 volt 3-phase 15 horsepower design beam motor. Go over to table 430.250. 15 horsepower is going to require 46.25 amps. And step 2, we take it at what? 125%. That'll give me 57.75 amps. Go to table 310.16, 75-degree C column. The next size above that is 65 amps, which requires a number 6 conductor. Pretty simple. Okay. But the thing I like to point out, did I change the calculation at all? No.
Nope.
The only thing I did different was get a different value. That's it.
Yeah, and I like that. You guys will be able to follow that coming through this. Is nothing really changes. Like, all they change is the theory and the calculation aspect of the values.
Sure. I had a guy that was taking his master's, and he struggled like 6 times before he passed the journeyman. I mean, he was really having a hard time. It was mainly calculations he was having problems on. And his dad was a contractor, and his dad called me. He goes, "I'm gonna hire you. I'm gonna have him drive to your house, and I want you to get him prepped for the masters, because he wanted him to be able to take over the company one day." And I said, "Sure, come on over." And I was going through laying this out for him, everything, and he went and took the test. Now, he struggled on the journeyman, but when he took the masters, he made a 92.
Wow.
And the reason was because he understood the process. And he called me. he said, he goes, hey man, he goes, I want to take you out. He goes, where do you want to go? I said, I was thinking about going to eat barbecue tonight. And so we went and had barbecue and had a beer and everything. And he said, man, I went in there, and he said, I was nervous as could be. He goes, but then I started he goes, the first question that was calculation, he said, I knew it. He goes, then I got it. He goes, I was thinking, God dang, man, this is easy. And I said, it's really not that hard once you understand the process. And like this in here, you got 40 horsepower, 3-phase, 460 volt design beam motor. Where are you going to go? Table 430.250. Every time I'm sizing what? My conductor's an overcurrent device. I'm at one of those tables. And then I only have a single motor, so 430.22 says I have to take it at least at what? 125%. Then you do that, then you got your amperage, then you go to table 310.16, find the next amperage size above it in the 75-degree C column, and there's your size conductor. Now, here's one where you got multiple motors. Everything's still the same. I've got 460 volt 3-phase motors here. Okay, I've got a 10 horsepower, 20 horsepower, and 30 horsepower. Well, I already know the 30 is going to be the largest, but I go to table 430.250, get all my amperages. So a 10 horsepower is good for 14 amps, 20 horsepower is 27 amps, 30 horsepower is 40 amps. Then I'm going to go down to step 2, and if I look at 430.24, the largest motor's taken at 125%. All the rest are at it at 100%. So 40 amps times 125% is 50 amps. Then add the 27 amp, the 14 amp motor, and that gives you 91 amps. Go to table 310.16. The next size above that, the 75-degree C column, is 100 amps, which requires a number 3 conductor. Now, was that hard?
No, and it brings up one question that I want to ask though. So, like, are single motors always calculated 125%? Is there any case where you could just take a single motor and calculate it 100%? Like, if it was like intermittent duty or something, maybe. But I don't know. I just
that's the only thing you would get into. You'd be looking at table 430.22E that gives you for periodic, intermittent, and those things there. That's the only place I know that you would get away with that. Matter of fact, we'll show that here in this presentation.
All right.
Okay.
Awesome.
And then when
I'm sorry, I'm not trying to predict the future on you.
Don't worry. You know, the great thing is we've been doing this for so long. I mean, between Dad and I, you've got over 80, almost 90 years experience, you know, in the electrical trade. And all these illustrations and everything everybody sees, that this is really pretty close to, I'd say, since we've been drawing, I'd say you're looking a little over 30 years that we have put a lot of technology into redoing all these illustrations and refining them. And, you know, like I tell everybody, well, go look at the other publications. Like, if you look at this illustration, look at all them sections in there. All the things we're telling you you'd want to consider here. Even though it's not what we're doing, it's just extra information there. Okay?
Yeah, and it's basically called a code loop.
Yeah, and
so
what I tell everybody,
you go back and double check and triple check and make sure you're on the right loop. And then as you're doing it, you're filling it out on the right-hand side of the screen, correct. And you're double checking it with the code loop.
Mm-hmm. And like I tell everybody, go look at other publications. You won't see this. And you know why? It takes a lot of time to go check all them sections. But it just goes to show the amount of work and effort and time we put into this stuff. And like this in here, we show 3 motors. You got a 40, 50, and 60. All you have to do is get the largest motor, which is going to be 60 horsepower, take it 125%, add all the rest, 100%, get your total amperage, go to table 310.16, 75-degree C column, find the conductor that's above it. It's that simple. Okay?
So is there any case where you would have to apply, like if you were under 100 amps, you would have to apply 110/14C1 for that? Like
well,
the terminals are unknown,
you want to go to C1B, it gets into the motors, and that's where you got the 75-degree C. But you got to you got to be careful because if it's an older motor, it could be 60 degree C termination, and then you would be
Gotcha.
using the 6 degree C column.
Would
That
there be anything if the terminals were unknown? Or is that just a general thing for motors?
well, if the terminals are unknown, it's based on the wire size going to it. Once you
Oh, gotcha.
make that determination, okay,
Gotcha. Okay.
and that'll be spelled out in 110.14C1A and B. Okay.
Gotcha.
And this in here, this deals with phase conversion. Now, what you're going to see is a little variance here from what we usually see. But this is where you're protecting the phase conversion on the conductors and everything. And they're going to tell you that the conductors have to be protected. In this case, you're still going to look at table 430.250 to get my amperage rating for the motor. In this case, we have a three-phase 20 horsepower motor. It's good for 54 amps. But if you go look at 455.682, it's going to tell you that it has to be taken at 250%, okay, for the conductors. Now,
Okay.
one of the things, well, I'm not going to do it now, but when we get into the overcurrent protection devices, anybody that's watching this, I want you to remember what I'm talking about here, okay? Because
Right.
what's going to happen is the uh, the conductors, usually whenever you take and I have a rule of thumb where I say if you size an overcurrent device at 125% or less, you go up to the next standard size. Any percentage above that, you drop down unless it states otherwise. And I give you two instances when I give that rule of thumb. I said you really have to look at phase conversion because it tells you it has to protect the conductors. And in this case, they have them going up to 250%, which is 135 amps, which requires a 1-aught conductor in the 75 degree C column, which is good for 150 amps. But when I size the overcurrent device, instead of dropping down, I would put a 150 amp overcurrent device there because in this section, it tells you have to protect the conductor. Okay.
True.
So,
True.
and the other one is when I get to transformers and it has a note 1 in there, but it gives you the option to go up or down. Okay. Because it
Right.
says shall be permitted. That's the only two places I'm aware of where you have to think about that. Okay. But when we get to overcurrent protection devices, y'all remember what I'm talking about here, that actually the conductor and overcurrent device are going to match up with each other. Okay.
So we have Raymond Quintero. Thanks for the like, sir. We have a motor that requires 230 volts, but we only have 208. Can the motor be connected? Ooh, excellent question.
Well, what he's getting into there, when you go over, and this was interesting because you'll remember this. Dad uh, went over this a while back. Remember we had him come on. He was talking about the motors and everything. And one of the things that we got into, and he was explaining to everybody, was when you look at those motors, they're 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 based on the frame of the motor and the
True.
voltages that are there. And that was one of the things he was getting into there, and he was talking about when you look at those, there's types that you're looking at. You got an induction type squirrel cage, and then you got round rotor. And when you come in and you look at that, it gets in and talks about the torque characteristics and everything. Well, uh, what they have when you get in, you start um, looking at that over in right on the side. It gets into talking about those different type of motors, and uh, I'm going. I'm going to do this off the top of my head, okay? Because I don't have it the table right in front of me here. I don't have my code book out. I usually do all this off the top of my head. So when you get over there, it'll tell you right where it has the horsepower on the left hand side. It gets in that talks about the falling values of full load currents, and it talks about what is typical for those motors running at those speeds. Okay, and then it'll have the currents that are listed shall be permitted for system voltage ranges. This is where you want to look at this. Okay. And what did he say? He had a 208 volt. Is that what he said?
No, no. So I've actually ran into this before. As a 230 volt, and they only have a 208 three phase. So it's a 230 volt motor, and to me personally, what I'm gonna say on this, Raymond, is the way I look at that is that's a nominal voltage. So as long as you have a nominal anywhere from 230 to 208, the only time I've had issues with that is when you have a demand, like a large demand. Because what happens is that 208 volts drops to like 196,
That's
and
right.
that 208 volts drops below that manufacturer recommended voltage drop, and then that'll kill the motor. So you have to watch that. Like if you're not on a high demand for that motor, like if you're able to, like usually the way you do this, you run the motor, you run it under load, and if you watch the voltage stay pretty consistent, then you should be all right. At 208, it'll run fine. Usually 230 rating is just a nominal rating. So we usually run equipment anywhere from 230 down to 200. It's just fine. But you have to watch that. We've seen European equipment come out that was 230 volt rated, and the equipment was trying to eat 240 volt. You know,
Hmm.
it was hungry for 240, and so you don't want to take that motor that's hungry for 240 and drop it down to 208. That's gonna damage the motor.
That's
But
correct.
in my experience, I've almost never seen a problem applying 208 to a 230 volt rated motor.
Yeah. Well, I can't even add to that. That pretty much summed it up. That's exactly how it works.
Yeah.
Matter of fact, we have in our generator transform motor compressor book, we actually have design notes in there where we talk about that. And then we go in and we also talk about the frame of the motor, because when you actually get into looking at the frame, that frame is set up for 220 to 240. Okay.
Right.
And because a lot of people would say, well, it says 230 volts there, but I have a 220 volt. Well, that's the frame. Okay. And that's why they have like a little thing over in the horsepower setting over explaining what that is. And you have a range
Right.
between there. Okay.
True.
So, yeah, that's true. Okay. And then
Thanks
this is
for the
one.
question.
Oh,
Thanks for the
yeah.
question, by the way,
That's
Raymond.
a good question.
Appreciate it.
Here you got a 25 horsepower motor. You come in and go over to table 430.250. It's a three phase, and then you're going to take it for 455.682 at what, 250%. And then you're going to size your conductor based on whatever your calculated amperage is. So everybody should be able to follow that just fine. Now, this one is where I'm getting in and I'm dealing with an AC unit. Okay. And here I've got a compressor with a full load current of 38 or 33 amps. And then I've got a condenser that has a nameplate of 2 amps. Now, I want to point out, you notice here, we're saying nameplate. Okay. The reason we're telling you it's the nameplate here is because when I'm calculating here and I look at Article 440, you're going to see that you are going to use the nameplate value, and I'm not going to go over and use the motor value that's given over in the tables. But the same principle happens here. You're going to take the largest at 125%, and all other motors are added at what? 100%. So
Yeah.
looking at 440.32, you'll see we take the 33 amps at 125%, gives me 41.25 amps. Then I add the 2 amp condenser on there. That gives me 43.25 amps. Then I go to table 310.16, pick up the 75-degree CCOM. The next size above that's 50 amps, which is a number 8 conductor. Pretty simple. Okay.
True.
So just remember, the first set we did was the motors there. We use the table values. Now I'm getting in to this. Now, some will say, well, why would I do that? let's address that right now, because this is a listed appliance. Okay, in other words, it's a unit. It's an assembly. Okay, it's
Right.
all been put together, and they know what's there. That's why you're using the nameplate amperage. Whereas I was doing individual motors, that's not part of an assembly where they put different motors in and created an assembly. In this case, an AC unit. Okay.
Right.
Now, as I look at this AC unit, same thing. I got 19 amp compressor and I got a 2.5 amp condenser. How do I do it? 19 amps is at 125%. The condenser is at 100%. Add all those amperages up. Then size conductors based on table 310.16 and the 75° C column.
Welcome in. Justin Gibbs is in the house.
Ooh,
Awesome. Thanks for
welcome,
having
brother.
you. Thank you.
Mr.
And
Gibbs.
oh man, he's got to go there. He's gotta poke the bear. So.
The answer would be
Uh,
no. You know,
yeah.
we've been getting into that quite a bit here lately on a couple of things, and you know, I submitted a proposal. I submitted many proposals, and I submitted them for one simple reason: I needed to establish in a location. Uh, it's hard
True.
to argue something when the location keeps moving all around the place, and
True.
uh, now that I have a location, now I can submit in the second revision and show where they got a problem. So, looking
Yeah.
forward to that. All right.
Yeah. No, I appreciate it, Justin. Thanks for joining tonight. Appreciate you, sir.
Now, this one, like I said, you take the largest motor at 125%, everything else is added at 100. Okay. So, let's take a look here. I've got three compressors. They're all the same, 45 amp or 42 amps each, and each condenser is rated at 3 amps. So you'll see in 440.33, I took one of the 42 amps at 125%. Everything else was added at 100%. See that? So
Yep.
add all of that up, gives you 145.5 amps. Go to table 310.16, 75° C column. The next size above that's 150 amps, which requires a 1-aught conductor. Now,
Right.
the thing I like to point out here, have I changed any of these calculations really? The
Yeah.
format, the layout, everything is exactly the same. The only thing you got to remember is how to do each one of them. But, you
You
know,
just got to be careful, like following James's, because you don't want to make the assumption you can just wire everything with a 1-aught.
yeah, this was just to go in and just sort of show how all this worked. You know, we
Yeah.
do it like this. We did in single line diagram because it's otherwise we couldn't get everything on here. But
True.
you know, we do show we got three AC units, and we're showing you all the AC units there. Okay, so basically, what would I do out there? I'd go out there, put me a wireway, and then I'd tap off of that for each individual one. See what I'm saying?
And
So
just to be a shout out to Justin in Colorado, none of them to be on GFCI protection. So.
yeah, not in Texas either. And of course, you know, by Jeremy's recollection of that, all of us here in Texas are nothing but glorified ditch diggers anyway.
Oh yeah, that was hardcore.
Yeah, I couldn't believe he said something like that. That's disrespectful.
Yeah.
I don't think he realizes how big our boots are down here.
Oh yeah. Oh
Okay,
yeah.
so this one, what you look at AC unit 1, 2, and 3, the largest is the 40 amp. Then everything else is at 100%. Get all your total amperage and size your conductor going over there to tap off of that to feed each one of those. All right. Now, looking at this one, what size overcurrent device is required on the primary side to protect the conductors and panel board? In the example, we had an example we were showing here, but this is very simple. I'm doing here uh, uh, showing a transformer here, and all I'm going to do is I had a 480 volt primary, 240 volt secondary with a 125 amp overcurrent device upstream. So we were just showing here how to do this calculation, And you do that, that gives you 250 amps. So I was going to size the conductors on that to protect the secondary conductors and the panel board that it was going down to. So if I had 250 amps, what's the next size above that? That's 255 amps in table 310.16 in the 75 degrees C column, which would have required a 250 kc mil conductor to supply that panel board. Okay.
225 is a standard size, or 255.
No, that's for the conductor amperage.
Oh, gotcha. Okay, so it's on 250.
Yeah, and then we're showing you here where you go to a panel board and you're protecting the panel board.
Oh, gotcha.
Okay.
Okay.
And this just gives you something to look at here to, because sometimes they throw this on the test to protect the panel board. So you just need that primary and secondary, then get the amperage upstream. In this case, it's a 50 amp. By the time you do it, we actually gave you the answer in the illustration. It's 100 amp, but we wanted you to know how we determine that, and this is how you do the calculation. So it's just a quick calculation for everybody to understand how to put it together. All right. Now, this one is where we're going to size the copper conductors that supply the secondary side of a transformer that has a continuous load output of 181 amps. Now, if it is continuous, I have to take it at what? 125%. And that, in this case, I'm going over, it's a feeder, so I'm going to apply 215.2 A1A, and that's where I get the 125% at. So I take 181 amps at 125%, gives me 226 amps. Then I need a conductor for that. Well, I go over to table 310.16, pick up the 75 degree C column. The next size above that's 230 amps, which is a 4-aught conductor. Okay?
Okay.
So as you can see, I'm just breaking down through this. Very, very simple. And the same thing here. I'm going to a panel board over here. I'm feeding it. Okay? I'm stepping down. All right? So how do I go about performing that calculation? All I need in this case is I need the kVA of the transformer, divide it by the voltage to get my amperage, and then I can start working on putting my percentages and everything in place.
Right.
Okay? And that's why I try to tell people, the way you go about doing these calculations is really not that hard. It's just knowing I've got to get the amperage for the transformer. Okay? I've got to get the amperage for the generator. Every one of those calculations are exactly the same. The only difference is if I had a generator, I had to put 115% on it. In this case, I had a continuous load. I had to take it at what? 125%. Okay?
Right.
So it depends on what you're looking at, but we try to cover every spectrum here so everybody knows where to find this information in order to perform this calculation correctly. Now, like this, and this is where I've got a capacitor. Okay? I've got a 460 volt 3-phase 10 kVA capacitor, and it's going to serve a 460 volt 3-phase 50 horsepower motor. Okay, and we're already giving you the information here. The motor is supplied by 480 volts, and it has number 4 THHN copper conductors. All right, so if I look at a number 4 conductor and I go over and pick up table 310.16 and come down the 75 degree C column, it's going to tell you it's good for 85 amps. So I'm going to take that at a third. And you'll say, where'd I get the third at? Well, you're going to go look at 460.8A. That's going to tell you to take it at a third. And that's going to give me 28 amps. Okay?
Right.
Now, what you're going to do, we're actually going to end up doing 2 calculations here. Okay? The first one is where we're calculating the conductors at a third, and the second portion of this we're going to be where we're calculating the full load current of the capacitor. All right. So in this case, I was at 28 amps. I go over to table 310.16. The next size above that's 30 amps, which is a number 10. Now, that's doing the conductors at a third. Now, also in 460.8A, I'm going to be looking at calculating the full load current of the capacitor. It's just like doing a transformer, generator, or anything else. I need to get the kVA of the capacitor, take it at 1,000, then divide it by the voltage. In this case, I have 480 volt times 1.732 for the three phase, going to give me 831 volts divided into that 10,000, and that's going to give you 12 amps. But it tells you there that you also have to take it at 135%, which is going to give me 16 amps. Okay?
Right.
Now, as you go in the second part of it, number 16 is going to require number 14. But you have to use the largest between the two. Well, if I
Oh,
go back,
you're saying 16 amps.
16 amps requires a 14. But if I look
Yeah,
at,
so you're going off the 75-degree C column, right?
yeah, yeah.
Okay.
And then when you come here and you look, which was the largest between the two? Well, it's where I calculated the conductors at a third. Okay.
Gotcha.
So therefore, the answer for this particular one going over to that capacitor is going to require me to have number 10 copper conductors.
Okay.
Okay. And a lot of people
Gotcha.
never seen that calculation, you know?
Nah, that's a new one.
Yeah. And we go through all this. Like we did the illustration here, you'll see from where the controller is and everything, we have one of the new capacitor units in there. These are actually a digital type capacitor assembly, and it digitally reads everything. Okay.
Nice.
And this here is the same calculation. I've got 25 kVA capacitors, three phase, 208 volts, and we're also telling you the conductors for the motor circuit are 3 aught. Okay, all you're going to do is the same calculation. You're going to do it based on calculating the conductors at a third, and then calculating the full load current of the capacitor. And whichever is the largest between the two, that's the size. In this case, THHN copper conductors you're going to use. Okay, so I think that'd be really good when there, because a lot of people don't deal with capacitors much. And then
Dude, 100%. That's
the
a good
next
one.
thing we're going to get into is looking at non-motor generator arc welders, motor generator arc welders, and also resistance welders. Okay. Now, the first one we're going to do is a non-motor generator arc welder. There's actually two ways to do this. Okay. And we're going to show you different methods, so you learn which one you like best and go from there. All right. Now, well, when I say two methods, it's when we're going to get into sizing the overcurrent protection device, because you're going to look at two different things there also. All right. So this case, I've got a welder that's 68 amps and it has a 50% duty cycle. Now, when you get to looking at the duty cycle for a non-motor, you're going to look at table 630.11a. But in 630.11a, we already know that the welder is good for 68 amps. We gave you the information. Then I go look at the multiplier that's going to be based on the duty cycle in table 630.11a. It's going to tell you it's at 71%. Okay. And the 71% is based on it being a 50% duty cycle. Then all I'm going to do is just calculate the 68 amps times 0.71, and that's going to give you 48.28 amps. Go to table 310.16, 75 degree C column. The next size above that's 50 amps, which requires a number 8 conductor. Okay. And then you come over here. Here you have a commercial type arc welder. We've redrawn these too. And you're going to see we have an 89 amp load and an 80% duty cycle. Step one, you got there, you got your welder, it's 89 amps. Then all you need to do is look at table 630.11a, pick up the 80% duty cycle, come across, get your multiplier, do your calculation, and size your conductors. Okay. And then when I get over here, this is a motor generator arc welder. Well, looky there, I'm doing the exact same type calculation. I've got 76 amps for the welder, and I've got a 90% duty cycle. I go look at table 630.11a, and it's going to tell. Now, I want to point this out. When I'm doing this for non-motor and motor generator arc welders, you're going to use table 630.11a. But when I get over and I start looking for the resistance type welders, you're going to look at 630.31a. We'll look at that in just a minute. So you'll
Yeah,
take.
and I think we had a good one come in, good comment come in that Danny mentions. The NEC gives you a direction to adjust ampacity if it's more than three current carrying conductors. So that's one thing you're gonna have to really look at. You know.
Oh,
Um,
sure. And we actually did that in an earlier portion of this, probably what, about 3 or 4 episodes before. And I went through all that and explaining
yep.
about the current carrying conductors and how to do the calculation for adjustment and correction factor or a combination of the two.
Absolutely, that's a good catch, Danny, because that's something everyone has to remember is this is not just a be all end all. You have to consider all these different temperature adjustments, everything. Like you can't just assume anything in the NEC.
Sure, if they're asking you a question on the test, it would be like this. But if they threw in current carrying conductors and all of that, then you need to consider it. But most of the
Yep.
time, you'll get a question like this, and you just do it like this, and you're good to
It's
go.
it's all in part of dissecting the question. You have to make sure you dissect the question correctly.
Sure, I always when I if I'm taking a test, I'm looking at plans or something. If I saw up, right here, there's 4 current carrying conductors. Guess what? I have a note there. That's something I need
Yeah.
to consider after I do this calculation.
Yes,
Oh,
sir.
it's in a temperature here. Up, I need to consider this. All right. So we had a 96.96 multiplier. Take that times 76, gives me 72.96. The next size above that's 85 amps in the 75-degree C column, which will be a number 4 conductor. Okay. And there you go. You got a motor generator. We got 65 amp load and 80% duty cycle. So step 1, 65 amps. Step 2, look at table 630.11, get the 80% there, come across, find out what the multiplier is, calculate it, and size your conductor. Okay.
Dude, have you been sneaking around my garage to get pictures of my welder or what?
I got some good pictures of everything.
Yeah, that's my welder.
Now, here you go. Here's a resistance welder. Remember, I said when we get there, you want to look at table 630.31A. We got 91 amp welder with a 40% duty cycle. Same calculation. 91 amps for a welder. Look at table 630.31A for 40% duty cycle. Come across, it tells you that multiplier is 0.63. Multiply that by 91 amps. That gives me 57.33 amps. Then step 4, go to table 31016, pick up the 75-degree C column. The next size above that, 65 amps, which requires a number 6 conductor. Pretty
Nice.
simple. And here's my resistance welder we have. I'm telling you, boy, we have really upscaled these illustrations. Now,
Yeah, it seems like you have all my equipment that's from my garage. That almost looks like my plasma cutter. I'm just like, where'd you get a picture of my plasma cutter from? You know?
I tell you,
But
we've actually done a lot of research making sure we get a proper illustration. And I'll say this: these look good, but when we finish the hazardous location and that equipment, that's pretty incredible looking. But we
dude,
are
I get the most amount of requests on my Nat King code page for hazardous location questions and stuff. So I'm gonna try to fool James with the hazardous location next week. So we'll see.
get after it. That's something I'm very
Yeah.
I'm when I started learning code, my dad started me on calculations and then he started me on grounding. He said, "You learn these two real well." He goes, "The rest of it comes easy." And then I got all that and I understood. And I've really put a lot of time and effort learning and asking questions. And then right after I got through that, he goes, "Now you're really going to learn." He goes, "This is hazardous." And boy, and
Yeah.
I spent about 5 years, I mean, really studying it. And I mean, I even got into going over, say, if I'm looking at NFPA 497 and you go over and look at the tables and you start dealing with your MIC ratios, your MSEGs. I mean, there's just so much in the table about the chemicals. I started learning about the chemicals. And then I even learned how to mix chemicals, put them in a group in order to help you determine locations and stuff. So
Yeah, I
It,
think that's funny that you're at dinner with Pops and he started talking about it. He's like, how'd you learn how to do that?
oh, that was the one when I did that. He didn't know that one. I was like, see there, you learn from us young bucks, you old fart. That actually happened. He was like, hell, I didn't even know that one. I was like, oh, well, there's a new sheriff
Yeah.
in town now. You need to retire, old man.
I knew who to call.
Oh man. But the reason I learned that, I was working with a chemical engineer that was helping me and teaching me that stuff, and he gave me books and everything. I started going in reading them, and when I got into that, I actually called him and I was asking questions, and it only took about 10 minutes before I understood exactly what they were talking about. And I was like, "Well, that ain't hard." He goes, "Yeah." He
Well,
said,
it's
"But a
just
lot of
based
people
on
get
the,
confused."
isn't it just based on the upper and lower level limits of
Not for that.
flammability?
Not for that.
Okay.
It gets into a little more than that because you got your maximum experimental safe gaps. You got your MIC ratio. I mean, there's more to it than just that. But the calculation is set up on percent of volume fill, and that's what you got to pay real close attention to. Right?
Okay. All right.
And then here we got a 100 amp load, 40% duty cycle. So you should know automatically in step one, it's 100 amps. Step two, I'm looking at table 630.31A, picking up my 40% duty cycle. Get your multiplier, multiply those two together, and whatever your amperage is, you size your conductor based off of that. Okay?
Nice.
And then this one, what this is going to get into, we're basically proving something here more than we are anything. And this is over in 430.72B2. Okay. And this is where they're going to get in. And like this first one we're going to talk about here, this is where they're sizing some THHN copper conductors that are permitted in a controller where the upstream overcurrent device protecting the branch circuit is rated 90 amps. Okay. So when you go over, you look at table 430.72B, column B, it's going to tell you 90 amps permits for number 14. But how do I prove that? Okay. And if you look at the bottom of the table, it's going to tell you that it's based on table 310.17, and I'm going to use a 60-degree C column. So when you go over and look at table 310.17, you pick up the number 14 copper conductor. It's going to tell you it's good for 25 amps. But right below that table there, it's going to tell you in note 2, it's going to tell you take it at 400%. And if you take 400%, that gives you 100 amps. See that?
Right.
Which permits the number 14 conductor. Therefore, that 90 amp is permitted to protect those number 14 conductors. Watching from India.
Oh,
Wow.
wow.
Man,
Welcome
we
in,
are freaking
India.
going worldwide, baby. Bam.
Man, we're international. We're
Bam.
international.
Well, Dad has done a lot of work overseas. And
Dude,
we
you even got a trophy in India, dude. See?
well, you want to hear something funny is Dad was over in Saudi Arabia doing a class. He was actually on the base there, and after the class, they took their cups and started hitting, just sort of going back and forth with a handle and hitting the table like boom, 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 boom. And Dad was like, "What the hell?" He didn't know what they were doing, and the guy come up and he said, "They only do that to show sign of respect for the best, and they're telling you you're
Nice.
the best instructor they've ever had out here."
Nice.
And I was like,
Okay.
"Really?" I said, "Dang, man, they don't ask for much, do they?" You
Mhm.
had to let Dad have it. So,
Yeah, that's
uh,
funny.
but this one here's an 80 amp, and you're going to do the same thing. You're going to look at table 430.72B2 and then look at that note 2, and then you'll go get those amperages and then put that percentage on there to verify that table 430.72B works exactly as they say. Now, and I do want to point one other thing out. The reason they're using table 310.17 is because you're in an enclosure here. And when you're within the enclosure, that's considered free airspace.
Right.
Okay?
I
So,
agree. Dude, that was the first time. That was probably like 3 weeks ago. Oh, watching from Belize.
damn,
Oh, dude, we were like hardcore international tonight, man. That's awesome.
man, wow.
Um,
Belize is nice. I've been to Belize. That's a beautiful place. I
yeah.
wish I was there. Matter of fact, I like Belize.
That was total new information for me when you brought it up. That you actually go off a totally different table with a 31017 because you're in open air. So your
Hmm.
ampacities, like even if you are like some people consider it bundling, even if you are considered to be bundling, you're in open air because that's not inside the cable. So
Sure,
you're
it's a
not
different
bundling the
thing at that
cables.
point. The
Yeah,
amperage
and
changes.
yeah, and I
It,
really enjoyed that. That was awesome.
well, it was funny. I remember when they were having that argument, and I said, "Well, now y'all can't do that." I said, "You have to take a couple other things into consideration." When I brought that up, it, what's that song? "The Sound of Silence."
Dude,
As,
I'll never forget when Weedman. I asked him the question like, "How can the utilization equipment be the outlet that feeds itself?" And he's a deer in the headlights, man. That was hilarious.
well, sure it is.
That was so funny.
Now, this is where you're permitted to extend beyond the magnetic star. So that means it's not inside an enclosure. In other words, I'm running a conduit over to it. Okay,
Right,
it's some type of raceway, and you'll see it says upstream overcurrent device protected to be 90 amps. Well, if you go over and you look in this particular one, it's going to tell you in table 430.72b column C. So now I'm in column C instead of B, and it's going to tell you 90 amp allows a number 10. But look at this. Now I'm going over there. I'm not in free air open space going over there. So now I have to use table 310.16, and it's going to tell you in note 3 to apply 300% on it. Well, if I
right,
take and look at a number 10 copper conductor, it's good for 30 amps. I take that at 300%, gives me 90 amps, and it tells you therefore 90 amp could protect what? Number 10 conductors. So
right.
it's proven the point there. And uh, I'm in high
Yeah, it
school.
looks like you got a high school student that's learning from us tonight. So
Yeah, well, that's what we're
awesome.
here for. You know, we
Yes, sir.
we provide it. Matter of fact, people that are interested in electrical, go over to the YouTube channel. It'll be under Stallcup Electrical Education. That's Stall and then Cup CUP. So Stallcup Electrical Education. That's the YouTube channel, and y'all go over and see all the videos. All we ask is you subscribe. It doesn't cost you anything, and hit the likes
Yeah,
and all of that, or
yeah.
smash those likes, Hulk like them, and
Crush them.
y'all
Crush the
can
likes.
you can go back and catch previous episodes. But we're trying to build that channel up. We've had it for years. We just never really pushed it, and
Yeah.
just in the last month, we added what 100 and something. I don't even
Oh
know how
yeah.
many we added, but
So our goal is 1,000 likes by summer. We're a quarter of the way there. So you know what I mean? Like that's easy to do. You know, we could get like 250 tomorrow if we just keep pushing. You know, so just
we don't
keep
really
put.
do it.
Yeah, it just just tell your uncle, your cousin, your brother, your like anybody in your family, like subscribe to our channel, and we're gonna hit 1,000 by summer, brother. We're
What
gonna
we're
see it.
trying. Now, if
Yeah,
you look at this illustration, see where I've got the control circuit conductors, but where are they going? They're going to a remote start and stop station. That's why you're not using table 31017, because you're got those control conductors going over there in a conduit. And that's why we're using table 31016. And then just do your exercise problem and put the 50 amps in there, and you know that once you go over and look at the table, it'll tell you what size conductor, and then you'll, based on that amperage, then you'll calculate it at 300%. Whereas if I was in the controller itself, I would do it at 400% because it's open air. Okay.
I'm gonna call this guy Raj. I'm gonna say, right on. Thanks, Raj. Appreciate you, Raj. You know. So
Yeah.
yeah, we're gonna keep
All right.
going.
Now, this and you'll know this one because we actually get into this where we're dealing with motors in 430.72C4, and they're basically going to clarify exactly what you're allowed to do. All right. Now, when you come in, they're going to ask, could 14 AWGTH copper conductors be used on the secondary side of a controlled transformer that has a primary full load current of 1 amp? This is your transformer control circuit. Conductors are inside control enclosure. The primary voltage is 480 volts and secondary voltage is 120 volts with transformers sized at 500 volt amps. Okay, so I'm going to take the 1 amp at 500%, and that's going to give me what? A 5 amp overcurrent device. Okay,
Right.
and then if I go look at column C in table 430.72B, it's going to tell me for a 45 amp motor branch circuit here that it could be connected to what? Number 14 conductors. So I'm going to
Right.
prove this point now. All right. So step 3, I'm going to take the 408 volt primary and I'm going to divide it into the 120 volt secondary. So that's going to give me a 1-to-4 ratio. Okay.
Okay.
So when I get in and I'm looking at determine the proper protection of those secondary conductors, I've got a 5 amp primary times a 4-to-1 ratio here, and that's going to give me 20 amps on the secondary. So if I go over and I look at table 310.16 and tie it in with 240.4D for my small conductor rule, it's going to tell me that number 12 copper conductors would be required instead of the number 14.
So
See that?
can I at this point call you a hack? No,
That ain't
I'm
a
just
hack.
kidding. I'm
Uh-uh.
just kidding.
But
You were
it's
trying to use 14 and you need 12, dude. Come
mhm.
on.
Well, that's why we show this is because
Nice.
somebody would naturally assume it was a 14, but you got to look at that because the way
Right.
that's calculated and everything, that might not be exactly correct.
True.
Okay.
I
And
agree.
then this one just gets into your control transformer. It's 1.5 amps. I'm not going to go through all this. I'm just work the problem and then we'll look at it next week. But I
Okay.
think that I'm almost done. Okay, I got just a couple more. This is just showing size and fixture wires here and how they can be used with a branch circuit that has number 14 conductors that are protected by a 15 amp overcurrent device. And we have a width from the junction box to the luminaire. Now, that junction box right there, that you can call it junction box, but it's also an outlet right there. Okay.
Dude, you know what's so funny about that? Like, do you know why they permit you to use like number 18 gauge or number 20 gauge, whatever it is, on the fixture width to the junction box?
Yeah, because it's already been listed and labeled in size for that size wire. They know how much amperage it's pulling.
Because it's technically a tap.
It's
It's a
not
tap. It's
really
a
a tap.
it's a
Uh,
tap conductor. So it's
I'd be
it's
careful calling that a tap conductor because,
well, I'm just saying that. Like, going from the outlet to the luminaire, it's you know,
well,
it's
you got to remember it you have an outlet up there, and you're coming out. You come from a whip, whatever, but when you get down to that fixture and everything, that to me that is I don't I wouldn't call it a tap because if you're looking at tap, then you've got to go over and apply the rules in 240.21B, and there's nothing in there that deals with that. Those are really considered tap conductors.
well. So I've actually seen this before in the luminaires where they say you cannot take that 18 gauge, go to a fixture, then go from fixture to fixture to fixture because it has to tap directly to that junction box.
Now I agree
So
with that, uh, Uh, well, yeah, because you got to look at that because if you're going from fixture to fixture to fixture, and you're using that number 18, you put too many of them on there, then that wire size is not large enough.
True. Yep.
I mean that would be where I would say that would be a problem.
I
Uh,
agree. I mean, I'm not necessarily calling it a tap, but the whole thing is it's technically how they size. I don't know personally the whole exact answer. I'm just saying from what I've seen, they're basically calling that a fixture tap to the branch circuit.
well, sure, and this. I understand the terminology, and that's why
Mm-hmm.
when you look at this, you've got 240.5B2 to determine the protection, and it's not in 240.21 because they're telling you here that number 18 can be protected by a 15 amp overcurrent device. So
Right.
they have kept it separate from there just for that reason, because some people may have called it a tap before. And the
True.
reason they rewrote Article 240 is to get away from that. So when people say tap, I understand what you're coming from as a terminology, just like we
Right.
used to say just tap the secondary of a transformer. They had to
Yep.
rewrite that so that wouldn't happen
True.
because people would size it different. Okay.
Absolutely.
And then here's a good example. Like I was saying, you had the luminaire that's there and you're coming over there with a whip. And this same thing here, we've got some known values. Got a 20 amp overcurrent device. You got number 12 conductors and number 18 conductors. Okay. Well, where are the number 18s? Those are where? That's going to be in the luminaire. Okay.
True.
So when they start looking at this and looking at the branch circuits, basically going to tell you that that number 18 can go up to what? That 20 amp connect to it.
Yeah, and it's gonna be it's gonna be problematic for them to call the inside of that luminaire the outlet when the 18 gauge is actually terminating at the outlet.
Mm-hmm. Well, and see, here's a good one. Well, what if I'm inside a pole? Okay. I've got two number 16 copper fixture wires that run 60 foot inside the metal pole and terminated to two number 10 copper conductors protected by a 20 amp overcurrent device. Can I do that? Well, yes, you can do that because if you go look at 240.5B22 and also tie that in with 410.30B, they're going to tell you those number 16s can be run that 60 foot and terminated to a number 10 conductor.
Right.
Okay. And, uh, but I can see what you're saying. Some say I can tap here and go up and feed all this. Well, I look at it more as they're nothing more than fixture wires. Okay.
Right.
And then here's one here. You got number 16 fixture wires with a 55 foot length pole with 20 amp overcurrent devices. What size conductors are going over there? Well, looky here. We're making you think here because I'm going all the way over here and I had to upsize those conductors due to voltage drop, and I've got a number 8 conductor. Can I do this? You see what I'm saying? So you got to
Mm-hmm.
go look at 240.5B22 to make that determination. Okay?
Yeah, and you'd have to bond with the number 8
Right.
minimum conductor too.
We're almost done with this thing, believe it or not. That's
Okay.
why I was telling everybody, 12 weeks, I'll try, but by the time we go through it all, it's really going to be probably close to 4 months before we're done with all this. But they're going to
Okay.
ask you here, what size overcurrent protection device is required for a branch circuit with a continuous load of 21.5 amps with 75 degrees C terminals? Well, all I'm going to do here, if it's continuous, I take it at 125%. So 21.5 amps times 125% is 26.8. We're just going to round it up to 27 amps. What is the next size above that for table 240.68? That's a 30 amp overcurrent protection device. Okay.
Right.
And then you get your illustration here. Same calculation. I've got 23.5 amps. It's continuous. I take it 125% and then size my overcurrent protection device for that.
Okay.
I don't remember how many is even in this damn thing. All right. Here's
Well,
one.
dude, the complaint department is like going wild right now. I don't know. I mean, this is your complaints that you're getting right now. Is
I
they're
know.
putting trophies in there for your complaints. So I think we're good.
Okay. Well, we got a branch circuit, has a continuous load of 100 amps. what do you take it at? 125% gives me 125 amps. The next size above that's 130 amps, and table 310.16 come across. It's going to tell you it needs a number 1 conductor. I'm going to protect the conductor in this case, which is going to be a 150 amp overcurrent protection device. Now, let's look at this a little bit further. Could I put 100? We'll just leave that. We'll just leave it at 150 amps. Okay. Here it is. I've got 90 amps. It's continuous. What I take it at? 125%. Then you size your overcurrent protection device and conductors based on whatever the calculated amperage is. That's for your homework. And that gets us through